90 palestras gravadas ali no canal YouTube.
Muito bom, eu vi.
Tem good morning, good afternoon, good evening. Thank you very much to join us again for another exciting IEEE Security Systems Society Rio Grande do Sul talk that is sponsored by IEEE Security Systems Society, also with the graduate program Microelectronics of the Federal University of Rio Grande do Sul, together with Brazilian Computer Society and Brazilian Microelectronics Society. So today we have the pleasure to have here Dr. Vladimir Alves, CTO at NGD Systems, USA. But before doing a short presentation of him, I just would like to invite you to next activities. So, also remind everybody that today the last day to the submission of proposal to do the master in the graduate program Microelectronics. And doing your submission now, you can really start your master in August, September, October, November, or December, depending when you finish your undergrad during these times. Then next week, the speaker will talk on Saturday because he's going to talk from China. So Professor Hao Kai from Southeast University in Nanjing will talk about energy efficient in MRAM computing. So another very interesting talk. Then August 6th, we have a Professor Roberto Gomes Garcia, University of Alcalá, Spain. He's a distinguished lecturer of IEEE Security Systems Society. He's going to talk about reconfigure the world, adaptive transfer function, and multiband RF filtering devices for emerging wireless systems. August 13 is time of Professor Luciano Agostini from Federal University of Pelotas, talking about video coding state-of-the-art and trends. August 20, Professor Małgorzata Czajanowska-Jeski from Portland State University, talking about heterogeneous integration, 3D systems, and emerging devices. Then the week after, we don't have the traditional CASS talk on Friday because it's time of chip in the fields with SBCCI 2021. By the way, Dr. Vladimir was the general chair of a past edition of SBCCI a long time ago. Very long time. It will be a virtual edition this time. Then week after, we have a talk by Professor Eduardo da Silva from Federal University of Rio de Janeiro, Brazil, where Vladimir was a professor a long time ago. He's going to talk about the new modalities for acquisition, representation, processing, and visualization of image, plenoptic functions, and light fields. Then I have also here the announcement of Professor Nader Bagherzadeh from University of California, Irvine. So this will be on October 15, some aspects of machine learning, computer architecture. If you lost the special event about assessment in higher education and research, the recorded version is already available in this YouTube channel. So the talk was done by Professor Michel Robert, former president of University of Montpellier in France, and the panel was had the participation of Professors Raimundo Macedo, Marcelo Lubazewski, Thiago Bari, and Avelino Zorjo. So all the recorded CASS talks from 2020 and several ones from 2021 are available in this YouTube channel, as well as a set of several other talks like the industrial talks done last year. So there is more than 90 talks recorded and available in this YouTube channel. So also in September, we have the third edition of the IEEE CASS Seasonal School on Sequencing System for IoT. This will run as a hybrid mode from Bordeaux. So you are going to see, if you go to the web page, you can see the preliminary program. Also in November, it's time of the 17th edition of the International School on Effects of Radiation on the Embedded System for Space Application. So we have to do virtual again this year from Porto Alegre. but we hope that next year that will be time to do it at CERN in Geneva, in Switzerland. Then will be a face-to-face one. Also, you have now a little bit more than 1 month to prepare your papers for LASCAS 2022. That will be this time in Chile. We hope to have a face-to-face conference, at worst a hybrid one. And as you know now, the best papers are selected to be published in TCAS 1 and TCAS 2. And the ones that goes to TCAS 2, they are published in the months of the conference. And the 2023 edition will be in Ecuador, and 2024 will be in Punta del Este, Uruguay. But today we are here to listen to Vladimir Alves, that is now CTO at NGD Systems. So Dr. Alves has been architecting and implementing solid-state storage solutions since 2005. Before founding NGD Systems, formerly NGN Data, he was most recently the senior director of SSD system-on-chip development at Western Digital, overseeing a team of 90 engineers responsible for the whole enterprise SSD controller design, verification, and validation. Vladimir was hired to build the Western Digital solid-state storage division. He has personally grown the system-on-chip team in US and overseas from the ground up in less than a year. His team is responsible for developing solutions for SCISE Express, NVMe and variable code rate, LDPC engines, among other key enterprise SSD controller IPs. Prior to joining Western Digital, Vladimir served as senior director of SSD system-on-chip development at Stack and was instrumental in developing the technology that put Stack in the leadership position as an enterprise providing SSD solutions. At Stack, Vladimir created and hired and led a team of 50 engineers in US and overseas, responsible for architecting and developing controllers for enterprise, industrial, and consumer-grade storage device. From 2000 to 2005, Dr. Alves was a scientist and director of engineering at Morpho Technologies, a startup company in California that developed an innovative architecture for a highly configurable and massively parallel DSP array used in high-performance signal processing for base stations. Vladimir obtained his PhD in microelectronics in 1992 from the National Polytechnic Institute in Grenoble, France. He subsequently held the position of associate professor at the Grenoble Institute of Technology in CERC, at Grenoble, France, Eurochip lecturer at the University of Aveiro, Portugal, and professor at the Federal University of Rio de Janeiro. He is the author of more than 30 scientific publications in the field of SoC architecture, computer architecture, semiconductor test, self-checking, and fail-safe design circuits. He is also the author of several patents in USA, Europe, and Brazil. And he was also, as I told before, former general chair of SBCCI conference in Brazil, and many other activities here moving to USA. So thank you very much, Vladimir, to accept our invitation to give this topic today in a very exciting subject. So the floor is with you to start your presentation.
Thank you very much for the kind introduction, Ricardo. This brings like a lot of memories from the past. It's good to talk to you again, and we had a good chat before, we entered online. I just realized how long this intro was, and I should have probably shared something shorter. But in a nutshell, what Ricardo said about me is that we, not just me, designed this kind of stuff, and I hope you can see. I don't know if it's aligned with the screen. So these are storage devices. And the difference is that they are solid-state storage devices, basically using only semiconductor components, which is basically the state of the art. Hard disk drives using magnetic media is still out there, but it's a technology that's being replaced by solid-state drives slowly in every area. There's maybe disagreements as to when and if solid-state drives are going to overtake completely hard disk drives, but that's a topic for another discussion. So first of all, again, thank you very much. Hopefully, I will bring an interesting topic to the table. That's probably a topic that few of you have heard of, if any. I'm going to talk about computational storage. So I'm going to start with a short introduction. I'm going to give a lot more details about what computational storage is. So these are enterprise class solid-state storage devices that are capable of processing workloads in the storage device itself. So we at NGD Systems, of which I am one of the co-founders, we basically specialize in the NVMe protocol, which uses the PCIe bus as a conduit, and to connect the host, the server's CPU to the storage devices, as well as other electronic systems that can be on that same bus, for example, GPUs. So solid-state drives can reside in many places. One of them is to connect directly to the PCIe bus. It gives you lower latency access, higher bandwidth to the CPU itself. So in systems where you use a massive amount of data, you store a massive amount of data, you would then connect multiple of those devices, typically to a host platform. And I'm going to give some examples later. But basically, continuing to what is computational storage, is the idea of moving compute to data. And to do that efficiently, we actually are performing or enabling the computation to happen within the solid-state drive controller itself, which is a chip, an ASIC that in our case we have designed ourselves because this feature was not present at the time in any controller available commercially. So by doing this, then we can perform computation on the data stored locally. And the way we've actually implemented this, there's a couple of other players in the market that are also providing and developing computational storage solutions. Our approach was to do it, do it within the storage controller itself, fully integrated, and in a way that it enables us to run an operating system within the storage device itself. In the case, we're mostly focused today on Linux, and once you have Linux running on a computing subsystem, then you can enable many other types of applications running locally, such as Docker containers for lightweight virtualization. You can run AI workloads, etc., etc. So I'm going to talk a little bit about that later. So the key attributes today is that we use standard protocols, so NVMe and TCP/IP, and I'm going to explain why TCP/IP is an important solution. And then we focused on an implementation that provides a seamless programming model. And to us, it was the most important factor. So that's one thing that particularly was important for us, and that we learned from past experience. In my case, I was one of the early employees at Morpho Technologies, a startup here also in Irvine, California, where I learned and I have some scars that programming model is one of the most important things when building a new type of computing solution. So the idea here is to exploit near data processing. And why? Because we're basically using that computational power to process data locally without avoiding the movement of data. And that's key because that's a way to save energy. A lot of the energy that's spent in any computing system is actually spent by moving data around. And then the other aspect is to exploit distributed processing. Because typically in computing systems, higher end computing systems, even at the edge, you'll find multiple storage devices for each CPU that are usually directly attached to the CPU. Not always, but usually directly attached to the CPU. So because you have multiple of those storage devices, then you can perform computation in all of them at the same time, so simultaneously. So you are able then to take advantage of the distributed processing aspect of this new architecture. And the goal is then to augment the system performance and reduce the energy consumption overall. So augmenting the system performance, because now you have more, computation capability, and it's proportional to the number of storage devices that you have. So it scales with the data growth, and reduce energy consumption, mostly because you avoid movement of data. So where does it come from? So I took the liberty here of showing a couple of slides from an interesting presentation that was made at Usenik 2019 by a few engineers from Intel Labs. And the computational storage, it's a long history. A lot of people, exploited or tried to exploit neo data processing, right? And obviously this distributed processing. You can see that things go back to the 80s, and there were proposals in the 80s of hard disk drives with some sort of computational capability and so on. Those never came to light, and mainly because of the fact that a few factors were missing. So one is the ability, with lower geometries, to pack even more logic within a single ASIC. And maybe we were not there yet with older technologies. And the fact that now with the cloud and edge, the amount of data that's being created everywhere, or at the edge and within the cloud, is growing, like really, if not exponentially, at least polynomially. So everybody says, oh, exponentially, but I'm not sure it's exponential yet, but it's really super impressive. So as of a noteworthy attempt was Seagate's Kinetic drive, which tried to create the first Ethernet, the first hard disk drive with an Ethernet connection, some computing capability, but didn't get a lot of traction, mostly because the hard disk drives are too slow, I think, in my opinion. And what's changed? I mean, I already hinted at that. Now there is a strong demand for very high capacity drives. So this is, I'm not trying to, make any type of advertisement, but this form factor here is for those who can see the video, is a U.2 form factor. It's very small, like as you can see compared to my hand. This holds 32 terabytes of data. The smallest one is a an M.2 form factor. It's the size of a gum stick. Holds 8 terabytes of data. So the trend is that everywhere people are storing more and more data, and it's more and more difficult, even legally, to get rid of data, to erase stuff. You have to keep everything for a very long time and so on. And there's more need to store more and more data. So there is a trend to kind of use more storage devices. So what did we do? We basically designed this little baby here, the controller, right? This is a 1,000-pin chip in a very compact form factor. We have two versions of it, the large one and the small one, mainly due to heat dissipation. So it's a relatively complex system that includes, as I'm showing here, from left to right, we have our, what we call the in situ stack, right, which is the computational capability that includes application processors, Neon SIMD machines from ARM, FPUs, caches, L1, L2 caches, etc. Then, as I move towards the right, I have what's the storage part of it, with several embedded real-time processors. They are mainly used for running the firmware, as opposed to the notion of software that actually executes the algorithm that is used to manage the flash media. Mainly manage the communication with the host that uses the NVMe protocol, the PCIe protocol, and then manage the health of the data that's stored in flash media. Flash is notoriously noisy, and errors can be created and so on. So I'm not going to go into all those details, but this is a huge portion of the work that we have done. So we combine the two aspects: the computational subsystem and the storage subsystem. And there is a little bit of a secret sauce that we don't talk too much about, is what gives us the ability to come up with a seamless programming model, meaning that the application processor, running on the computation side can access seamlessly the data that's stored on the flash media at the same time as the host is doing that. And I'm going to have a couple more diagrams that will explain it better, but let me jump into what we designed. We at the time the chip was taped out, it was, I think, the most aggressive design in terms of geometry for an SSD controller. We designed it and manufactured it at Global Foundries using a 14 nanometer FinFET. It had roughly 9 megabytes of memory, embedded memory, close to 136 million gates, and runs typically around 4.5 watts, depending on for a typical workload. It can go higher depending on the workload, meaning how many accesses are being made from the host to flash, flash to host, etc. So that keeps varying. So this is kind of a typical workload. The RTL code for that was entirely written in Verilog, test benches, etc., written in System Verilog, and we just disclosed there's no problem with that we use 100% Cadence CDA tools from beginning to end. Cadence, by the way, provides a lot of support for startups, and in our case, we are truly still a startup. It was a very important kind of support that we got from them. So now I can go into the next slide, show you guys the result. So as I said, we manufactured we manufactured it's the same die, and it can be packaged in two different form factors. So this large package that you see on the left has a higher pitch and has also a lid, and that lid helps with dissipating energy. So for the use cases where the power consumption is higher, then we would use this type of package, but it limits us on the size of the form factors, right? The smaller form factors will call for the smaller package size. Okay, so how does it end up becoming like a solid-state drive, right? So we call this type of solid-state drive, or you give the name computational storage drive. So it's a solid-state drive that has computational capability. We implement drives. For example, in this case here, you see the SSD. They're depicted on the right side with the controller, DRAM, and the flash media on the other side of the board. These are the main components. The rest would be regulators, PMICs, all sorts of QSPI, small memories, etc. that are. But there's three main components: the DRAM, the controller itself, and the flash media. Just to for those who are not probably may not have been able to see that in detail on the camera. So here are, as an example, these are the types of products that today we sell, right? This is in production. There are other form factors out there. These are the most important ones, and those are the ones that we're focusing on. So the U.2 is similar in size as an HSD, as an HDD, so it's 2.5 inch. The M.2 is in a gum stick form factor. It's the smallest one that you find, and as we said, we can achieve up to or put up to 8 terabytes of data in there using flash, TLC type flash, and the E1S with up to 12 terabytes of flash. So E1S is like a newer form factor that's promoted by OCP. For servers that are being used in the cloud data centers in general. So this is kind of replacing, in a way, M.2 and U.2. There's other form factors that are coming, E3, S, and so on, all sorts of different form factors, but they're all similar in the way that they connect to the host via a high-speed, serial connect. And the main concern is increase the the storage capacity and take care of heat dissipation, because there's a ton of heat that's generated on those storage devices. So I'm gonna make a quick pause here, just double checking with Rico if there's anything that I need to. If there's a question that we need to address right now and so on, I'll be happy to. Otherwise, I will continue with my presentation.
So maybe you can leave the questions to the end of your talk.
Sure, absolutely. Yeah, I was just giving the opportunity. How does the computational storage work? So I'm going to have a couple of pictures here that's going to try to explain the concept, right? So this is kind of upending a little bit the traditional paradigm for computing. So we're adding a type of resource that was not commonly available before in the realm of heterogeneous computing. So this has become more and more common first with accelerators that were mostly sitting in the PCIe bus. You'd see, compression accelerators, encryption accelerators, etc. Then GPUs came in also sitting on the same PCIe bus to help enhance the performance of systems. Very, very powerful subsystems, but that consume a lot of energy. And what we're doing here is adding computational capability that's very close to data to perform some specific functions that would augment the performance of the system. So you see here on the left side what I call the hardware stack on the left side. So with the connection between the storage device at the bottom being done with PCIe, the PCIe protocol. So you have hardware engines that deal with the PCIe and NVMe protocols. And then we have a few blocks here, modules that are entirely dedicated to the computational storage aspect of it, our 64-bit application processors, SIMD coprocessors, other hardware accelerators that can be instantiated to augment even more the processing capability. So you have the real-time embedded processors, as I said, for example, the M-class processors from ARM or others like RISC-V processor, etc., that are used to implement the storage functionality, right? So I highlighted in blue the things that are new that are related to computational storage. And those that are not highlighted are what you would find normally in an SSD. So we have internal buffers, error correction engines that are super complex, and all the media interface that needs to be programmable, parameterizable, so that you can handle multiple types of flash media, because there's multiple manufacturers. They're not all the same. They don't behave exactly the same. So on the right side, you have what I call a software stack, right? So on the host, you have the typical, stack with, and obviously oversimplified here, but just to give you an idea, an operating system, you have the file system, and you have your application running. And we do provide a sort of an agent, so very simple executable that helps you connect with the drive from the computational point of view. And in the next slide, I will explain a little bit better how this works. So the idea is that the entire application or a subset of it can actually run inside the drive, right? And because we have an OS, then we can give the same support that you would have on the host side. And it can run also on multiple drives at the same time. So if your data is residing here locally in this flash media, then you can run this application, something as simple as a search, more complex as a compression algorithm, or even more complex as like machine learning algorithm. Anything in theory can run there, and you have the limitations are related to the amount of memory that you have locally and the type of processors that you have, right? And then you also have a ton of firmware that's needed to manage the solid state drives here. So you see here firmware that's related to the PCIe NVMe protocol, firmware that's used for the flash transition layer, flash manager in general, flash microcode that runs the flash media interface, and so on and so forth. So diving a little bit more on how this works. Again, this is a very high-level picture, but it helps a little bit explaining what's going on. So you see here on the left side, the server host processor with CPUs, or maybe even a GPU, etc. And you have within the host OS, you have your application running, right? And then you connect this CPU to the storage devices using an NVMe protocol that runs over the PCIe bus. So reads and writes are done through that pipe, which is a very high-performance pipe. Several gigabytes per second, depending on if it's a PCIe Gen 3, Gen 4, how many lanes are there. But we're talking like very high bandwidth and relatively low latency using the NVMe protocol. Are there other storage protocols? Yes, but NVMe is clearly taking over all the legacy ones. On the computational storage drive, you have the entire part here, what I'm representing in a simplified way called the media controller that controls the NAND media with some DRAM that can be shared. And you can basically run this as a normal solid-state drive, right? You're performing reads and writes that go over the NVMe protocol, get to the media controller, and then access the NAND media to write or read from, and then provide the data that the host CPU needs to execute the application. Now, what we did is that we added this, computing subsystem that in this case was an ARM quad-core. It could have been anything else. This is just a design point. It could be a RISC-V, it could be an octa-core, it could be a single core. But the concept is the same. So the architecturally doesn't make any difference. It runs its own OS, and it can run either the same application that's running on the host or a different one, right? The idea is to augment the performance of the overall system. So you can say, well, I'm going to let the host still continue to run its stuff and so on, but I'm going to accelerate by running something else on the drive. Or it could be the same, and it can run in parallel. Or it could be a subset of the application that is running on the host. In this way, you have to kind of change that so that a subset of it runs locally. It's the programmer's choice, right? And it depends on the problem that you're trying to solve and how much you want to augment the performance of the system and reduce the energy consumption. as I mentioned, there is a host agent, or we label it in this slide host API, but I will have to change that. It's probably better to call it a host agent. That basically handles the interaction between the two operating systems, right? And to do this, we use the tunneling. So we create a TCP/IP link between the two sides by tunneling TCP/IP packets over the NVMe bus. So every OS, including Linux, obviously, knows how to talk TCP/IP right out of the box. So we didn't want to implement a lot of proprietary solutions in our case. So our implementation of computational storage heavily uses existing, proven standards, protocols, interfaces. So this is one of the ways that we made the programming model very seamless, is that we create this TCP/IP link that goes like hidden, a tunnel through the NVMe bus, right? And right off the bat, one of the first things that you do when you start using our version of computational storage is that you can, on the host side, create an SSH connection between the host and the computational the OS running on the computational storage drive, and open a terminal there and just start playing. You can run shell commands and get going already doing computation. You can write a quick shell script and search your entire media, for example, using those processors here. So let me continue here. So I'm not going to spend a ton of time here in this slide, but basically what we did is that we build an entire stack, and that stack starts from the flash, right? We provide a very solid enterprise-grade solid-state drive, and then the idea of building a computational storage the way we did was to add the storage devices in a way that integrate very seamlessly with the rest, right? And you can actually run an operating system. You can run a shared file system so that both operating system on the host and on the drive, they can access the data simultaneously. And this way, we enable on the software side, we enable like the basic stuff that allows you to run containers, that allows you to run Kubernetes, microservices in general, and then there's no limit. I mean, we are running Chia for crypto mining, Apache Parquet, MongoDB running like in storage, right? TensorFlow, Elasticsearch. There's no limitation. The limitation is that our specific implementation, first implementation, has X amount of memory, and this type of microprocessor. That's what limiting us in terms of architecture. It's a whole world that's opened up right there. Just a quick look at the software stack, and that's a little bit of an eye chart, but I wanted to kind of highlight that if you look at the software stack on the host side, it follows the OSI, the typical OSI model, and that we replicate that on the Newport computational storage device. And that's, I think, that the big differentiation of our solution with regards to others in that are also competing in this computational storage market, namely Samsung and another startup called ScaleFlux. And we're very happy that they are in the market, because this proves that computational storage really is a needed type of solution to tackle the growth of data at the edge and in the cloud. But I think our differentiation there is that because the programming environment that we provide in the computational storage device itself is so much similar to what a normal programmer sees on the host, that the only thing that he has to be aware of and skilled at is in distributed processing and and be aware of where the data is, and that's it. The rest is like identical to what that programmer would see in a normal environment running on an AMD or an Intel CPU with a Linux operating system. So that's what makes the big difference. Now, I want to. For us, it's kind of important to look at the cost, because we're a startup. We're not just doing research, even though research. It's not. I'm not trying to be negative or demean the research aspect of it, but for us, cost is super important. And we've published a paper late last year on the ACM transactional storage. So I encourage you guys to take a look at it. It's easy to Google it. It was a very good study with Microsoft Research, and also involving our colleagues at the University of California at Irvine, as well as the Federal University of Rio de Janeiro, which is my alma mater. So we're working in conjunction with these two groups to develop a lot of interesting work around the applications that can run on computational storage. So we want to develop the ecosystem and so on. So we're doing a lot of basic research on that. So that paper was kind of the culmination of a couple of years of work with these three partners: Microsoft Research, the Federal University of Rio de Janeiro, and the UCI. Professor Bagherzadeh, which we're going to present, as Ricardo said, in October, has also been working with us, and we are co-authoring other papers with him as well. So basically, from a cost perspective, with what we are highlighting is that integrating it all in a single ASIC was a key factor of reducing the cost significantly of the computational storage, solution that we are deploying, and that's very important. The other solutions out there on the market use FPGA, which is there's an interesting approach to that, but the drawbacks are related to programming model and cost. And I'm going to zoom in a little bit. And in this paper, we do a high-level study of how that cost can become like acceptable for most users when we switch to a fully integrated in single ASIC solution for computational storage. So just jumping here a little bit, a couple more things that I wanted to say. So just for you guys to visualize where this technology can be used, and I'm not just talking about ours, but any computational storage approach can bring benefits at different levels in the cloud, in the infrastructure that's sitting at the edge. And I know everybody has a different definition of edge and so on, but let's say it's, a relatively high, in this case, relatively high performance, mid-size or small deployment of computing resources away from the cloud. So you can call them nano data centers or small computing, clusters out there. And computational storage can also be very relevant, very close to the edge itself, right? So right now, we are deploying our drives in autonomous vehicles that need to store a gigantic amount of data, and we're helping those manufacturers of these gateways that are deployed in autonomous vehicles to populate their gateways with a ton of storage devices. And that brings me to the next slide, where you see the typical computational storage field deployments. Maybe for some of you that are not super familiar with it, I'm giving a couple of examples just to give you an idea. This is a 2U server with 24 NVMe slots, right? This is a very common today form factor. Things are changing. U.2 is kind of changing slowly and so on. Today, this server deployed with the maximum capacity storage would contain 768 terabytes, just that machine. And obviously, if we're using our Newport computational storage drives, that would come with an additional 96 CPU cores inside those drives. And that can be very helpful. Now, if you imagine that those come typically in a rack, and the size of the rack depends on your deployment. So you can see how this adds up quickly in terms of maximum capacity, in terms of storage, as well as number of CPUs that you're adding. And those CPUs are residing very close to the data. The other type of deployment that's super interesting is these types of data recorders / gateways, etc., that are being embedded inside autonomous cars, right? And the M.2 form factor that I showed, the size of a gum stick, this is a super compact. It's one of the most efficient types of formats today. With 8 of those, you reach 64 terabytes of data. That's probably enough for 1 day of data acquisition, according to what we've been told. So this is how much data is being collected out there. So I'm gonna check for time. How are we doing on time, Ricardo?
It's okay.
It's okay? Okay, sounds good. So I'm gonna talk a little bit about use cases. So I brushed quickly that because we enable the usage of an operating system within the drive itself, within that controller, right? Then you build on top of it, right? With an OS, you can build Linux, then go from there to Docker, and that's it. And then you start building on it. So as an example, the other day somebody came and said, "Hey, can we run MariaDB on a drive?" My response was, "Hey, I've never tried. I'm not sure." So with a little bit of research, we found a Docker image, official Docker image of MariaDB, compiled for ARM. That's it. In 30 minutes, we were up and running and executing stuff. So it can be that easy, but it can be complicated. Obviously, if you need to, for some reason, modify your application, etc., it can be complex. But that's the normal programmers, paradigm, or the work that they have to do. I'm going to briefly go over some examples, like starting away from machine learning and then dive into machine learning a little bit. Full disclosure, and I'm not a machine learning expert. I work with a lot of people that are machine learning experts. For example, I'm imagining Professor Felipe França from the Federal University of Rio is in attendance. I've been working with him a lot, and he's been helping us a lot in this field. He's an expert. But I'm going to talk mostly about the results, what we were able to actually achieve. But happy to eventually try to help to answer some questions that might come up at the end. So let's start with a simple example of compression, right? So if you're storing data, you think about, okay, I'm storing a lot of data. Can I compress data? Yes. I can use the CPU. It's very time consuming, energy consuming, etc. Can I use the computational storage to compress? Yes, the answer is yes. And that's something that at the very beginning of our journey, we experimented with. And we can show that as you have increased the number of what I'm calling devices here is the number of computational storage drives, if they're operating as SSDs, right, I'm limited to whatever the CPU, my host CPU can do, right? As I enable them as computational storage devices, I can have my little processors inside each one of them to do a little bit of compression in addition to what the whole CPU can do. And this is what we show here on the left side. This graph shows how little by little, as I add the number of computational storage drives, right, to my server, my compression rate increases significantly. And the energy consumption doesn't grow as much. It grows a little bit and doesn't grow as much as you would expect, mainly because of two reasons, right? That's what's shown in the right side. One is that the ARM architecture, and I would say RISC architecture in general, because I would expect to see the same thing from a RISC processor, a RISC-V processor, for example, is notoriously more energy efficient than the traditional Intel CPU. And the other reason is that whatever is compressed locally to the drive reduces the amount of data that needs to move from flash into the PCIe bus, into the memory bus, so that the CPU can compress and then maybe write back, right? So that's a lot of energy that is saved. So whatever you compress locally, you don't have to move that data, right? So that's one typical, simple example that can exemplifies a little bit what we can do, but it can be a lot more complicated. There's I think we have in our website a white paper, so those who are interested can either contact me later, or I can find the white paper about using computational storage for Elasticsearch. So Elasticsearch is an application that does distributed search. So basically what we did is that we're running Elasticsearch both in the host and in the storage drive. So that's what we call hybrid mode. And we can show like a significant improvement in performance and a good reduction in energy as well. But Elasticsearch can also run in what we call the CSD only mode, meaning that the CPU could be doing some other task and leave the Elasticsearch task, which is basically a search on the data, to the computational storage device. So your system performance improvement would come from the fact that you free up the CPU to do other tasks, right? So it's obviously dependent on what kind of problem you want to solve, but that's something that definitely can be done. So moving on to another type of example that now starts to use machine learning. It's in-story machine learning for drive reliability. So now I'm looking at one way of using my computational power to run more efficiently some algorithms that can help predict the health of my drive and manage that health more efficiently. So this is the work that we've been doing with a team at the Federal University of Rio de Janeiro, so led by Professor Felipe França. We have one PhD student there that's very active at it, Victor Cruz. So hopefully he's gonna finish his PhD thesis soon. But we're very happy to collaborate with them. So basically, what we are trying to do is in the process of managing the health of the NAND, one thing that we have to do is decide what is the threshold voltage that we're going to use for the reads to the flash media. And that seems to be a simple problem, but it's a very complicated problem actually when you are using the type of NAND flash that we use, which is the TLC and QLC flash. Those are very noisy, very complicated flash memories to use. It requires a lot of expertise, and usually you invest a lot of effort in designing like algorithms that are in nature very rigid, that helps you predict what is the next threshold voltage, VT voltage, that you're going to use to perform your reads on a specific die or block within all of those that are in your array of flash, right? So what we're doing, so what Victor is doing under the supervision of Professor França is to move from this very rigid type of cooking algorithm that doesn't give you flexibility and requires a lot of trials and errors, is to use machine learning to learn from the behavior of the flash, and as the flash, let's say we can call it ages, as it gets used, it will change in behavior. It will generate more or less errors, etc. And we use machine learning to predict, okay, what is the trend, so that we can correct the errors more efficiently. We've obtained so far very, very exciting results. They haven't been published yet, and I think we're going to be doing that in the next few months. It seems like very exciting. So it's perhaps it's going to be one of the first commercial SSDs to have like such a machine learning engine to help predict the health of the flash. Now that I've touched into machine learning aspects, I'm going to talk a little bit about some work that we've done in computer vision. So I mentioned that ACM transactional storage paper, transactional storage journal paper that we published. A lot of it was actually, all of it was focused on computer vision problems, right? We obviously discussed computational storage in general, architectures, comparison with other approaches, and so on. But all the experiments were running over computer vision problems, right? Mainly object tracking and image similarity search. So in object tracking, we did a very good work there. And that work was actually, a lot of it was done by the PhD, Felipe's Professor Francis' PhD student, Victor Cruz. So he was working on running different types of algorithms on computational storage to see, first of all, if we're capable of actually even functionality-wise implement those object tracking algorithms inside the drive itself, and see if they were, we could run them. And those range. I'm going to present in the next slide. It's going to be a little bit clearer. And then we did a study on the energy efficiency of this approach, and showed how computational storage increased the energy efficiency significantly while maintaining the overall accuracy of those machine learning implementations for object tracking. So this graph here that I kind of zoomed in from the previous one, right, shows here how the computational storage implementations are yielding like extremely low power, high energy efficiency results, while maintaining the accuracy compared to the implementations running on CPU and even on GPU. Now, obviously, you cannot compare the performance, for example, to that of a GPU, but the idea is to, again, to add to the overall performance of the system and reduce the energy efficiency. So that work is kind of detailed in this paper. For those who are interested in that, you can take a look at that paper, and I'm sure the authors, including myself, will be very happy to answer questions and discuss with you guys. Now, continuing exploring that, one of the PhD students from UCI was kind enough to help me out with a couple of more slides that are there towards the end of this presentation, to talk about some of the work that he's done on machine learning, implementation of machine learning algorithms using computational storage drives. So those are relatively large deployments that we can afford every so often. So we have racks of a couple of racks of servers here that we can populate those servers for a certain period of time with a relatively large number of storage devices that can operate either as simple SSDs or computational storage, and then that's where we can run those experiments and so on. So we keep using this infrastructure to explore all these algorithms and these like proof of concept experiments, right? One of the interesting things is I liked this diagram that I kind of worked on with him for one of the papers that he published at ICCAD, I think, last year, where it shows that typically on the left side, the part A, right, is the typical model that you have. Like you have an application server that's running your whatever machine learning workload that receives queries and provides outputs. And then that, those applications there, will send requests for data, right, to the storage devices. Data is transmitted from the storage devices to the application running on the CPU, right, on the server itself. And then the output is provided back. So what we do here when we introduce CSDs is that mix, right, where queries are still coming from the outside world, but they can also be, because we have the computational capability at the drive level, you can forward those query requests directly to the computational storage devices so that computation can happen locally. But also requests for data can also be sent. So it's a mixed workload, and every workload is going to behave differently. You're going to see, more or less improvements. There's no way of predicting, or at least we haven't found a way of predicting before, actually giving it a try. We can, guess, but usually you have to try it out to figure out how much improvement you get. And sometimes that mixed of, workload works very well, sometimes not so well. So you'd see, different types of work. But in most cases, or actually, I think in most cases, you see an improvement, either huge or medium or low. In some cases, you don't see improvement. That's very rare. What he did, and with the help of because he's a PhD student at UC Irvine and as an intern here. So he gets the help of all the engineers while he's working to set up his stuff and discuss the approaches, etc., review the results and so on. So what he's been working mostly in distributed training, looking at data parallelism and model parallelism. So the idea with computational storage is that because you're aware, or if you can be aware of what the data is, you can work on data parallelism, meaning that you know exactly where your data is residing and how it maps to each computational storage device. So you can perform training locally and share, the metadata, so like weights and things like that, and the model parallelism uses the same type of approach where each machine, even including the computational storage device, has a portion of the model and treats a portion of the model, right? So in how this works in practice, so this diagram on the right side here shows like a host CPU with its memory there at the top that's connected to a PCIe bus that runs the NVMe protocol. So all your storage devices that are there to store your massive amount of data for your training session, right? Training activity is going to have, so all these storage devices are going to have the ability to help you with the training and using like a federated learning scheme to kind of augment the performance of the whole system. This approach has already been shown to be very effective. I think a long time ago by a team at Google. And Ali, our PhD intern here, was able to kind of reproduce some of these results at the level of computational storage devices in multiple servers. So the type of results that we get is similar to the first one that we saw in terms of the compression algorithms that were running on multiple drives. As you add more drives, you get improvement in performance. You can see here, for example, on the top on those graphs, as an example for MobileNet and SqueezeNet, you can see that you quickly gain significant performance by adding the computational capability of each one of the local cores. And then the energy efficiency also improves. So the energy per image drops because a significant proportion of the data transfer is eliminated, and therefore the associated energy that goes with those transfers is eliminated. So the more detailed discussion on that is provided with on that paper. I think it's mentioned in the previous slide. Yeah, this one is a DAC paper from last year. Oops, sorry. Apologies. So same thing actually can be said for inferencing. So actually, a lot of the interesting results that we get is when we're doing running inferencing, and the same concept applies. I see actually, personally, I see a lot of value in actually focusing on inferencing rather than training for computational storage devices. But we've had this discussion, and in some cases, I think it makes sense to tackle to address training as well, possibly. But inferencing seems to be a very good way of applying computational storage to machine learning workloads. So let me jump here to the results. So the last work that he's working on and hasn't been published yet, but we are going to share a couple of results, was on natural language processing. So things like the sentiment analysis. There's an interesting data set from that's shared by Twitter that can be used to run proof of concept or benchmarking. Context recommendation, for example, movies. There's also examples and benchmarking sets for that, and speech to text. So he ran in the same type of environment as before. Let me see if I can show that. The typical, let me see if I can go back here. Typical type of setup that we have been using for these experiments is the one on the top, with 2U servers, like from your typical server providers that run on either AMD or Intel CPUs, dual CPUs, high end, lots of memory and lots of drives, right? So up to 24. So that's how we can show, the scalability when the number of drives increases. So the experiments that he ran on natural language processing were very, very encouraging. No hit in accuracy. So he was running a distributed implementation. He got, on the best case scenario, like a speed up of 2 to 3x, depending on the use case, with some gain in energy efficiency as well. So that was very encouraging. So he's continuing that, and probably, obviously, focusing on trying to get a paper published with these results, and that's about it. So I'm leaving here one of the papers that I talked about for the previous slides as the one that we published at the DAC. So it talks about low power acceleration of deep neural network training using computational storage devices. This is a paper that can also be used for those who are interested in learning more about how computational storage can be used for this type of application. So before I end my talk, I would like to say that there's a lot of other activities that we're experimenting with, developing platforms for small satellites. So we're partnering up with we have a grant from the U.S. Space Force, and we are partnering up with small satellite providers to use high capacity computational storage devices in deployments on orbit edge computing. And we also have a very, very interesting proof of concept and joint development with VMware. So last September, VMworld was still virtual, and so September last year. But we had a 1-hour presentation with a group of the office of the CTO at VMware. And they're developing their edge analytics platform, that new edge analytics platform, using computational storage. And in this presentation, they've talked about how computational storage can, change the way we're doing edge analytics, and how we are working together to integrate computational storage within their approach for edge analytics. So that's another very hot topic, very interesting for those who are interested in knowing more about what can be done with computational storage. And with that, I think I've ended my talk. Maybe, I don't know if I'm still have a lot of time left, but I'm happy to answer some questions and chat, and I can go back to slides if need be.
Okay, thank you very much, Vladimir. Very nice talk. So we have here some talks. First one is from Aaron Ray from ST Microelectronics, New Delhi in India.
Hi.
So hi, are you taking both on-die and die-to-die variation while training the threshold voltage to be projected?
Very good question, and very knowledgeable person, I believe. Yeah, yes. So the approach will lead us to the point where we can track variations from die to die. You can imagine that the flash media array that we have has multiple dies, and I can show here. This is a typical example. You can see those multiple flash packages. So within each package, there's multiple dies. And then within a die, you have multiple blocks. So the approach would let us track those variations down to the block level, meaning that even within a die, from block to block, you may have variations over time, with temperature, et cetera, et cetera. So yeah, the goal is to track this as much as needed. So we don't want to overdo it. So we'll experiment and see, okay, how far do we need to go, right?
Thank you. So now we have a question by Rafael de la Rosa from Universidad de Sevilla in Spain.
Mm-hmm.
So hello, Vladimir. I wonder about the effort related to the migration process of an application developed for a traditional architecture to a distributed architecture using computational storage.
Yeah, excellent question. So, yeah, this is a very valid and very good question. I'm going back to this slide here to try and help answer that. if you're trying to take advantage of distributed processing, inherently there will be issues. So just imagine that you have an application that runs in one computer, and suddenly you're faced with the conundrum of having to deal with a lot more data. So you can buy many more computers and store more data, or you can buy an appliance with storage and so on. If you buy an appliance and grow your data, you have one computer, you have a bottleneck. That computer still has a hard time, will have a hard time processing a lot more data, right? But if you buy multiple computers and you spread your data around, you have a distributed processing capability, but it's hard to figure out how to do that. So that's for example, what has been done with MapReduce and Hadoop, right? So these are frameworks that have been developed to enable you to run, processing in very large scale over multiple processing units. So there are problems that are very easy to tackle, believe it or not. So, for example, if you are talking about running facial recognition on, faces that have been captured, you can just instantiate whatever facial recognition software you want to run on each computational storage drive and start processing there, right? And you're going to have matches or hits or miss or whatever, right? So that would be a very easy way to go about. And same thing with compression. I can just start compression processes, but other applications are a lot more complicated. And there's no good answer to your question. Some applications are going to be a lot more complex. As I shown in some of those slides, you can actually incorporate computational storage into a Hadoop framework. So Hadoop automatically deals with the distributed processing aspect of it. If you are ready to use Hadoop, you can use it. And I can incorporate a computational storage device into a Hadoop cluster to help with the overall performance of the system. So I hope I was able to kind of answer that. There's no clear and crisp answer. Sometimes it's easy, sometimes it's as complicated as in any computing system.
Thank you. So now a question by Professor Rafael Brum. In the next CASS talk, that will be next Friday, same bat hour. So Professor Hao Kai from China will talk about research on in-memory computation at device level, building on the memory arrays. What are your thoughts about that?
I find it super interesting. I think that the way things are evolving, right? The way the data collection is evolving, the way the edge infrastructure is evolving, we will need to add a lot more new tools, new strategies, new architectures to solve that problem. I do believe in my heart that computational storage is one of them, and I think that in-memory processing is also going to be one of them. And those are not going to be competing because they're going to tackle different problems. And I see some value. I think in-memory processing is still going to be a little bit challenging to from the cost effectiveness point of view. And some people may agree or disagree with me, but I think that adding that extra logic to perform computation within the memory die itself is challenging from a cost perspective. But it doesn't mean that the concept is flawed, and it doesn't mean that it will not be cost effective in a very near future, right? But I do believe that these are two of the technologies that need to be incorporated in systems in the near future.
Thank you. We'll now have a question of Thiago Alves, that is professor at the University of the State of Rio de Janeiro, former Philips students. So his question is, has there been any experimentation with hierarchical trees of CSDs for image hashing-based database, for instance?
Okay. No, not yet. But that sounds interesting. We have two. The answer is no, but I want to just say a little bit. So we have two sets of activities in terms of the exploration on applications and the usefulness of computational storage. One that's driven by our customers. They come to us with problems, and then we tackle that. The other one is our interaction with the academia. And ideas come, and then we discuss, and we see, okay, is there a potential to benefit our ecosystem in general, right? So if we see a potential, then we make the decision. Okay, should we start an activity there? But the answer is not yet. And if you have ideas, just let me know. Shoot me an email, and we can chat.
Thank you. So now a question by Professor Cláudio Gayer from Federal University of Rio Grande do Sul. So there are already real edge systems or applications using your storage hardware or similar papers with performance evaluation?
So, okay, the answer is kind of yes. Obviously, I want to be positive about it. We are already in production. So there's customers using our storage devices in the field, and we're selling it as a product, fully validated, etc. Right? So yes, it's out now. It's still in its infancy for all of the players in the computational storage market. Right? A lot of these deployments I can't talk about publicly because of non-disclosure agreements. I think the most exciting one, as I said, is the one with VMware, because we publicized it. We have an entire session at VMworld that talks about it, and it is exactly on that topic of edge analytics, and that's pretty much real. So yeah, it is real out there, and that talk is obviously a video, and I think with the papers that we published, there's enough information for those who are curious to know, get more detail than what I revealed.
Thank you. So Rafael de la Rosa, thanks for your answer, and he has another question. Does it exist any tools which analyze the memory usage of an application in order to help in the implementation task for achieving the best performance possible?
No, not a specific tool. There are tools, performance analysis tools, memory analysis tools, and so on, that are commonly available that people use according to their preference and the availability, and those are usually the starting point of a study to see whether computational storage could be beneficial, but nothing specific that has been developed just for that purpose.
Thank you. So Cláudio Gayer, Professor Cláudio Gayer is also asking if it be possible to send hardware for scientific testing at UFRGS or Brazil in general.
Yes. So the theoretical answer is yes. The complicated aspect of it is that those are expensive, right? And for us as a startup, we have limited ability to provide like free loaners, etc. But it is possible. We can consider that. So we're not like NVIDIA that has a lot of money in the bank, and sending a couple of GPUs here and there doesn't hurt them. For us, it's a little bit more complicated, but in general, we're very open to the interaction with the academia. So we try to make it happen as much as we can, right? And actually, I think our interaction with the academia is only limited by the bandwidth that we can assign to that, right? Because the way we operate our culture here is to foster this type of interactions. So it just so happens that UC Irvine is close by. The Federal University of Rio is my alma mater, and I maintain still a strong relationship, for example, with Professor França over there. And that's the reason that a lot of our, the papers that I talked about and the research that I talked about comes from these two places. But we've been discussing with many other institutions. And we do the best we can as fast as we can. As a startup, this is one of the challenges of being a startup is the limitation in resources, and you have to be creative to go around this. But yes, Claudio, we can give it a try. If you're interested, let's have a chat.
Okay. So there is many congratulations here in the chat. Don't have time here to read all them, but one is from Ali Haidari Gorsh from UC Irvine, nearby you. Professor Sergio Bumpi also thanks Vladimir, excellent presentation. So he's sending his congrats now from Germany.
Oh, he's over there. Okay. Yeah, and this presentation is truly not like a presentation. It's something I put together, and it's not something I present every day or prepared for a paper or something, right? So I'm just really talking about our everyday life and so on, with maybe a little bit fancier slides, but not that much. It's really truly what we do. I hope in general people found it interesting and opened up the curiosity for computational storage. This is very important for us as a startup, but also the other startups that are our competitors, that people get interested in computational storage, right? So I encourage you to reach out, and we'll do the best we can to kind of disseminate the information about it.
So I see no more questions in the chat, but I have a final one. So some applications are very critical, as the automobile ones that you are that you talked about.
Yeah.
So nowadays, the chips, mainly the modern ones, are very sensible to radiation effects, even in the ground. No. So what are your considerations about the effect of radiation in your chips?
Yeah, excellent question. So we are going from the ground up. As I mentioned before, we do have a grant from the U.S. Space Force, and one of the goals in this project is to test our subsystems, right? The drives themselves in radiation environments. So we already went through two rounds. The one is called the total ionization dose. The other one is the single event upset. And we did get some very interesting results. The 14 nanometer FinFET technology that we use is very resilient. We found some issues in voltage regulators that are notoriously prone to be sensible to radiation. And for space deployments, we will have to revisit the choice of components because of that behavior. But overall, we're very excited about it. So we to be honest, we did not design to be radiation tolerant, but we're doing the test to identify what the weak spots are to go through a next maybe revision in the near future to see if we can make it even more resilient. And there's more and more technologies now that are being developed for shielding that we can use as a combination for heat dissipation and protection against high energy particles. So I don't know if you guys can see still the video, but this is an example of the E1S. So the E1S is this form factor. It actually ships with a case, right? That case is a metal case, and mainly designed for heat dissipation. But it can be manufactured with the right alloy that will give you the protection you need in certain environments, like at low Earth orbit or a different type of orbit. So we're investing in that. So we're still in the beginning, but yes, we're looking at those aspects.
Very interesting. So thank you very much, Vladimir, for this very nice talk with very interesting achievements that you have in your company. Congratulations.
Thank you very much. It was a pleasure and an honor.
For us. The invitation. Yeah. Thank you very much. So several other congratulations that you can see in the chat channel, also from Felipe França and so on. So thank you very much, and thank you all to attend this very interesting talk by Vladimir. I will just remind you about next events. So it was already told. Next week we have Professor Hao Kai, Southeastern University in Nanjing, China. So his subject is more or less related. So it's about energy efficient in emergent computing. So I hope to see you all next Friday, same hour, in this same YouTube channel. And the week after, we have a talk by Professor Gomez Garcia from University of Alcalá, Spain. And Roberto is a distinguished lecturer in the program of IEEE Sequencing Systems Society. So thank you very much. Then after that, we have a Professor Luciano Agostini from Federal University of Pelotas talking about video coding, state-of-the-art and trends. So we have already several talks scheduled till the end of November, and I hope that you reserve this hour each Friday to attend these talks. So thank you very much again, Vladimir, and all the audience that attended the talk today. Bye-bye. See you next Friday.